All right. So actually, wait, no. I want to. How many trends do we have for our periodic trends? Like, what are they? Can someone name them for me?
Are you talking about the SPD? Yeah.
No, we're talking about
Uh,
module 12, periodic trends.
Oh, 12.
what she said.
First ionization energy.
All right. My favorite. Just kidding. Okay.
And then there's electron affinity too.
Ionization energy.
And
I
electron
write big.
affinity.
Electron affinity. Okay.
Electronegativity and atomic radius.
Nice. Electronegativity. I don't know how to spell. And I just realized I didn't actually need to write this out, but that's fine as long as you guys know. Electronegativity and atomic radius, right? So I'm going to start from the bottom up because as we go up, starting with atomic radius, it will just start to slowly click, hopefully. I don't know. So for atomic radius, you guys all know what a radius is, right? Like, you need to make sure because it's been a while since geometry, even for me.
Yeah.
All right, so like atomic radius, let's say we're trying to see how it gets bigger, right? So when it gets bigger, what's the word I'm looking for? When it gets bigger, what would be bigger? What?
Yeah, you got there. I was gonna say, ask them to tell you how to draw an atom.
Well, they already said it like last time. I don't want to just keep throwing the same thing at them. But okay, this is like our protons and neutrons, whatever. All I'm focusing on right now is the electron shells, which we all know, because we had to use it for Rydberg's equation. So which would be bigger, an atom with 2 shells or an atom with 3 shells? What do you guys think?
3 shells.
3 shells, right? Okay. Okay, well, 2, so let's get rid of that one real quick. So 1, 2, 3. So all these all have like a whole lot of electrons in the center. 1, 2, 1, 2. Those are all electrons. Let's say this one has 2 electrons on its outer shell, and then the right one has 1, 2, 3, 4. It has 5 electrons on the outer shell. Which one will be bigger? The one with 2 electrons or the one with 5 electrons?
2.
The one with 2 electrons. Okay, well, why do you think it's 2 instead of 5?
Well, I'm going based on the little arrows thingy.
The arrow thingy?
Yeah, like I know that it's
Like
like
force?
to the left side and like the first group. I know they're like the biggest because they have like 1 electron.
Oh, okay. Well, but these aren't
Yeah.
on the periodic table. We're just drawing them randomly. They're not drawn as
These
they
are
would be
just
on the periodic table.
we're just going over the basis for it, like what it means for it to have a bigger radius. So normally the more there is of something, the bigger it is, right? Like that's what we're used to. But obviously that's not the case here. So you've played with magnets before, right?
Yeah.
At least once in your life. So let's say we have ourselves like a little magnet here. I use bar magnets because those are the ones I know best. So let's say this is a minus, plus, a plus, and a minus, right? So these two, are they going to attract to each other? Or are they going to repel?
Right.
They're going to attract, right?
Yeah.
Okay. So if we put another smaller magnet in between, there's a plus on this side and a minus on this side. what's that little magnet in the center going to do to these two magnets on the side?
Repel. Yeah, push them away.
It's going to repel them a little bit, right? So,
Mhm.
so if this magnet right here is bigger, is it going to push these two further away, or what do you think?
I mean, if it's bigger, I'm guessing it's stronger. I don't know, but I don't know how magnets work.
Yeah.
I'm guessing that's how it
Just
works.
use that mentality. Just use that mentality.
Then it,
So if it's bigger, is it going to repel them more or bring them closer together?
if it's bigger, it should repel them.
Okay. So what if we left that one the same and then we make this one smaller? If we make this magnet smaller, is it going to be repelled more by the center magnet or be closer?
Repel them more.
It's going to repel
Wait.
it more, right? So since this one, wait, what?
No, yeah.
Okay.
I'm
So
just
since
adding more logic to
one
the
is-
question, and I don't want to do that.
Oh, no, it's fine. You're going to see the correlation right now. So since this one's smaller, that means that it's has less of an attractive force, right? There's less of a minus to pull it towards that plus. So looking back at these two electrons have less of a minus, but there's still all these other minuses that are in between this outer shell and that nucleus, right? So it's going to be pushed out a little bit more compared to this one with 5 electrons. The more electrons on the outside, the greater the attractive force towards the nucleus. Does that make sense?
Mhm.
All right. Is everyone else good with that? Everyone, does that make sense to everybody? Because I know my boy here, Sebastian, is gonna like get this down packed. You know, he's asking these questions. He sounds good. But like everyone else, are you guys good?
Okay, so it depends on the valence electrons?
Yeah, it's all based off the valence electrons.
Okay, that's
Yeah. So like the less valence electrons there are, the more those core electrons, or the ones that are closer in, push it away. So since it's being pushed further away, it will have a bigger radius. Does that explain it better?
yeah, and then it's because of the shield, what is it called? The shield effect too, right?
Yeah, that's
exactly.
exactly what the shielding effect is actually, yeah.
Okay.
So the shielding effect is those core electrons telling these outer electrons to get out because they want all these protons to themselves. So they're just pushing them further away. All right, so we figured out the basic trend. So the less electrons there are, the bigger or smaller the radius
The more
for the
the
valence electrons. Okay, so the more valence electrons, the smaller. The more energy levels we have, bigger or smaller electron radius, atomic radius.
it should be smaller since they are getting attracted. If going based on what you said, I think.
For energy levels?
Yeah,
No,
well,
no,
for
for the
atomic
energy levels.
radius.
If there's more energy levels,
Is there more
yeah,
energy
will it
level
get
that should
smaller or
attract
bigger?
more? I believe it should be smaller.
Okay, remember energy levels means shells. So if you have more electron shells, is your radius
Okay.
going to be bigger or is it going to be smaller?
Wait. So
Oh, it's gonna be bigger.
Oh yeah, well you got in another like we said it
get
should
more
be.
shell, it's gonna like yeah, exactly. Because since energy levels are shells, the more like if you add another shell, it's obviously gonna be a little bigger.
Yeah.
Or well, not obviously, but it should be bigger. Okay. Before we go into the next thing, just gonna look at the. So as you can see, you know, it's real colorful, it's pretty. So let's say we're looking at carbon,
We
right?
still see your whiteboard, Jerry.
Oh, I thought I changed it. Can you see it now?
Nope.
It says I changed it. Do you still see a whiteboard?
Oh, there it is. There it is.
Okay. So we see carbon right here, right? So carbon, second energy level. There's 2 rows, has 4 valence electrons. If we compare it to silicon, which one has a bigger atomic radius?
Silicon.
Why?
Well, no, they should have the same. Yeah. Oh, wait.
What
It
makes you
has
think
more
silicon
energy
has a
level.
bigger?
Silicon.
Yeah, it has more energy levels, right? That third shell is a lot bigger than that second shell because it has more electrons it needs to hold. Okay. Well, what about, let's say we have sodium and we have aluminum. Which one will have a bigger atomic radius, aluminum or sodium?
Aluminum.
Okay, why do you think aluminum?
Hmm.
Based off of what we just said, with the
'Cause, yeah.
whole more electrons, less electron stuff.
Oh, so it's sodium because it has less valence electrons?
Well,
Yeah, since there's
so
less
it
valence
depends
electrons,
if
it's
it
gonna
got
be
to
further
be
out.
added, right? Another ring to it. Like another.
No, yeah, if there's another ring added, it's gonna be bigger.
Yeah.
That's what those energy levels are. And if there's less valence electrons, it's also going to be bigger because that shielding effect, like Edwin was saying earlier, is pushing it further out. Does it make sense?
I'm not sure now.
Because remember that electrons are always constantly, they have like this internal conflict. They're constantly struggling between trying to stay as close as possible to the nucleus while at the same time trying to stay as far away from other electrons as possible. So the more pull you have into the nucleus, so the more protons that you have in the nucleus, the easier it's going to be to pull all of those electrons closer to the nucleus. And in the opposite direction, if you have more electrons, the harder it's going to be to get closer to the nucleus, but the easier it's going to be to spread out away from each other, and that's going to make your radius bigger. Does that make sense?
I'm okay. Oh, it makes sense. It's just like I'm not sure if
So
it's
if
going
we
based
have,
on like adding another ring to it.
if you add another ring, that's gonna, I mean, that's like making, I don't know.
Because we're talking about atomic radius, right? And
Yeah.
I believe aluminum should be bigger.
Yeah.
Because we added another ring, I think.
Okay, but aluminum compared
okay.
to sodium, how many rings does sodium have?
3?
How many rings does aluminum have?
Okay.
I don't know. 3, 2, 4.
Yeah, so we can't compare them because they're on the same, remember the periods tell you how many rings you have, right? So if sodium and aluminum are on the same period or the same horizontal line, they have the same number of rings, right?
Oh, I get you. Okay.
So you can't use the ring argument when they have the same number of rings. So now, because we said there's 2 things that determine the radius, right? The number of rings and the number of electrons. Basically, top to bottom size increases and left to right. Left to right, it decreases. Yes, and that is, and the reason why is because remember we said the more electrons you have, the more you spread out in the radius, right? So who has more, who has more, it's valence, what's happening right now? Jerry, help me.
Okay, so what's called, every time we add another shell, we're pushing those, we're trying to push that outer shell as far away as possible. So every time we add another one, it's going to be further away than the previous one. So if we have 4, that 4th one is being pushed as far away as possible. Well, that 4th one is going to be further away than the 3rd one that element already has. So when we're looking at one that only has 3 shells, that 3rd shell can only be a little further away than any other 3rd shell. Does that help, Sebastian?
Yeah. No, if anything, I'm getting confused with the rings, but it's because from what I know, it's supposed to be, it starts with 2, then 8, right? The first ring is 2, the second one's 8.
Yeah.
Okay, I see what's happening.
Yeah,
Yes.
with how many electrons it can hold.
Yeah.
Yeah. And the third one should be
You're overthinking it, Sebastian. Just so you know, you're overthinking.
It's not that deep. You don't have to think about how many electrons you're holding. You have to think about how many containers you have to hold electrons.
So, based off of everything we've said, the atomic radius increases based on how the arrows are going right now, right? Pushed away by other electrons, so why it gets bigger. And then the more rings, I guess if you want to call them that, there are the like it's gonna be, because like you're just adding on top of each other. No, let's say I have like this little ball of napkin, right? Because this is the closest thing in my room. So I have this ball of napkin. Let's say that's one shell. If I put this paper around it, is it bigger now?
yes.
Okay, that you can think of it the same way. Let's say I get another napkin and I put it around. Is it bigger now?
Yes.
So every time we add another shell, we're just adding another layer on top of it. So it's gonna get bigger and bigger as we add more.
Okay.
Makes sense? Sound
Yeah,
good?
I get you. It just
All right. I'm gonna go
I'll
back
see later on because we may see it later on, so I'm just gonna wait for now.
All right. So the next thing that we're gonna talk about is literally my favorite and the most important thing in chemistry, electronegativity. So for electronegativity, well, I guess before we talk about it, does anyone happen to know what the most electronegative element is on the periodic table?
Fluorine.
Fluorine, right? And
Yeah,
it's like up here in the top right, you know, it's just not minding its own business. It's super clingy. We don't know why. Well, we do, but we don't talk about it. So for electronegativity, well, let's talk about fluorine a little bit since it's the most electronegative. How many valence electrons does fluorine have?
7.
7, right? Oh wait, that's that's a circle. 1, 2, 3, 4, 5, 6, 7, right? These are bad circles, but they're circles. So it has 7 valence electrons. How many more does it need to be a complete shell?
Uno.
I just gave away my next question. But how many?
1.
It needs 1, right? So it needs 1 more electron. So, okay, it needs 1 electron. Is it easier to pull? Okay. How are we pulling in this electron? Let's go back to the atomic radius with the magnets. What's pulling electrons towards the center of the atom?
Protons.
Protons, right? So is it easier to get to the protons if it has 2 shells or 3 shells? Let's try that. So like, let's say we're looking at chlorine. So this is fluorine, and then we're looking at chlorine. Oh, there's another one. 1, 2, 3, 4, 5, 6, 7. So is it easier to reach these protons in the center if it's bigger or smaller?
Smaller.
Smaller, right? Because it's not that hard to try to get as close to those protons as possible. So that's how we know that fluorine is more electronegative than chlorine, right? Since fluorine is smaller than chlorine. So we just said that if it's smaller, that it's more electronegative because it's easier to pull in that electron. We all agree on that, right?
Yeah.
Okay, so with that logic, okay, if we, is it easier to get 5 electrons or 2 electrons? What do you guys think?
It's easier to get
2.
to.
It's easier to get 2, right? So if we were to look at at oxygen compared to like lithium, it'd be easier for oxygen to get 2 electrons than for lithium to get 7, right?
Mm.
So with that in mind, let's go back to our lovely periodic table. Yay. Oh, that's not what I'm. There we go. Okay, can you guys all see the periodic table?
It's
Not
still on
yet.
the whiteboard. Oh, there it is.
He has a delay. That's fine.
Okay. I'm just too quick.
Yeah.
All right. So, okay. Well, since we said that the smaller it is, the more electron. Wait, what? Okay. So we said that the smaller it is, the more electronegative it is, right? So that means if we go upwards, it's going to be more electronegative. Okay. And then we also said that the less electrons it needs, or the more valence electrons it has, the easier it is to pull in like 1 or 2 more electrons, right?
These are the arrows I was talking about.
All right. Oh, these are the arrows you're talking about?
Yeah.
Wait, you said the arrows make sense, right? Or you
Yeah.
were doing it based off the arrows? Okay, okay. As long as the arrows make sense, that's like the first step. Well, the first.
That's why I mean,
Yeah.
like when like
So,
the first group was technically the biggest.
oh, no, okay. So
I think I was confusing
for
with
atomic
something.
radius, it's the other way around.
Oh, I get
Yeah,
you.
I think you got it mixed up with one of these, but that's fine. That's fine. You know, this is a learning process. Well, obviously,
Yeah,
because you know we're
so
at school.
all of them,
But
of the 4,
huh?
all of them except for atomic radius increase up and to the right, and atomic radius increases in the opposite direction, so down and to the left.
That's why. Isn't
Uh,
it like francium like the biggest?
Yeah. Francium's considered the biggest because, you know. Oh,
That's what I mean.
actually,
Like,
well,
yeah.
francium's down here, you know.
It's because what
So,
I meant is like it has like because you know how we're like talking like the more like never mind.
I don't know, like, okay, you know, okay. So, before I continue, what is everything on the periodic table included in these periodic trends? Yes or no?
What? Wait, what?
Are
So
are all no, all elements aren't included on the periodic trends, right? So which ones aren't included?
Transition metals?
I think it's copper, but no, I don't remember.
Oh wait.
Okay, what okay, so what are okay, let's use electronegativity for a second. So for electronegativity, what's the point of all these elements? What are they trying to do?
Well, for trying to gain electrons.
Okay, let's say they're trying to gain or lose, but like what are they all trying to do as an element? When they become ions, what are they doing?
They're trying to get 8 electrons or get balance. So be like a noble gas technically.
Be like a noble gas, right? Okay, so if all these trends are with the basis that they're trying to be like noble gases, can noble gases be included if they're trying to be like themselves?
No.
No, right? So
Oh, I get
we
you.
don't
No.
really we don't care about these guys all that much. I mean, we care about them, don't get me wrong, but like
Not in this
eh,
case.
yeah, not in this case, exactly. So with that in mind, okay, we know what the most electronegative element is. Which one would be the least electronegative in this case then?
Hydrogen? Maybe.
Uh, based off of periodic trends, or like based off of what we've said so far. We said
Oh,
that
no,
the
noble
bigger.
gases.
No.
Oh,
So for periodic trends, we said that the bigger it is,
Yeah, I'm
the
thinking it's francium too then.
Yeah, it would be francium. Yeah. Wait, I can't see the chat. Can you say?
It's Emily. She said francium. Yes, Emily. But
Dang,
why the question
Emily,
mark?
nice.
We stand confident students.
Oh, that's why I can't see it. Okay.
Be confident in your answers, guys. Even if they turn out to be wrong, it doesn't matter.
Yeah,
Most
be
of the time you
aggressive.
guys are right. Most of the time you guys are right. So don't. Okay, I'm gonna shut up.
Well, I'm not gonna say that, but like, if you're right, or if you feel you're right, you can like talk me down or be like, hey, no, you're wrong. I'm perfectly fine with that, as long as you can back it up at least, So, okay, so we figured out atomic radius. We figured out electronegativity. Any questions on those two?
Yeah.
You're all good? Everyone good? Everyone feel smart?
Wait, so what elements have the less electronegativity?
Oh, Emily has said it earlier. So it would be francium. So as a rule of thumb, atomic radius and electronegativity are inversely related. So the bigger the atomic radius, the less electronegative it is. The more electronegative an element is, the smaller the atomic radius. Because electrons want to go to something that's small and easily accessible. If something's big, it's hard to get to its heart, Like you can think of it as I don't know if you guys like watch movies or like Marvel, but like big guys like Thanos and stuff like that, in order to reach his heart, you gotta like put some emphasis in that compared to like a human, I don't know. It's something like that. That's how
Okay, yeah,
electrons are.
that makes sense. Yeah, that makes sense.
All right. So the next one we're gonna talk about is ionization energy. And ionization energy, it's not too bad. It's not too bad. Okay. So for ionization energy, can you see a whiteboard?
Quick question. For the electronegativity, the arrows are pointing up and to fluorine, right?
Mm-hmm.
Okay,
You know why, right?
Yeah. Making sure.
Yeah. All right. Cool. So for which one was I doing? Ionization energy, right? So for ionization energy, is it easier to take off? Wait, actually, before I even say anything, what is ionization energy?
Like energy to take an electron out, something like that.
It's the amount of energy to take an electron off, right? Yeah. Okay. So ionization energy. I don't know why I put a parentheses. Ignore that. I really suck at writing, but yeah, ionization energy to take an electron off, right? So what is easier to take an electron off? If there's one electron in the valence in the last shell, or 7? Pretty extreme, but still.
One.
Yeah, it's easier to take off one electron. It's easier to steal one than to steal 7 from something. So just keep that in the back of your head real quick. So if for ionization energy, we're literally just gonna think of this as stealing. I don't condone it, but stealing's like a really easy way of thinking about this. So, let's say we have like a little fortress or like a castle or something. And like, here's the royal people with their pluses and positives and money or whatever. And then we have like the minuses, which is like agriculture and stuff like that. So if we have more and more land, is it easier to steal crops and cattle from it when there's more land or less land?
More land.
More land, right? So like so in correlation, the more shells there are, the easier it is to steal. It's not like the protons won't even know you stole one of their electrons until it's too late. Likewise, since there's like what we said earlier, when we are only trying to steal one electron compared to stealing 7, it's a lot easier to steal the 1, because like all you're doing is like a grab and dash. You just go take the electron and you're already out. So with this mentality, gonna go back again. So which do you think would be the hardest to steal from? What element do you think would be the hardest to steal elements from or electrons from?
Noble gases.
Ignoring noble gases.
Then the halogens.
Okay. Out of the halogens, which do you think would be the hardest to steal from?
From those? Or
Based
like
off what
not
we
counting those?
said. No, from those. Yeah, from those.
Isn't it fluorine there?
Yeah, it would be fluorine.
Fluorine,
Yeah, you can kidnap. That sounds way worse than stealing, but that works. Okay, but yeah, so actually, I like that one. I'm gonna keep that. Okay,
Yeah, you can
so
have something
yeah,
from it.
fluorine is. Okay, so fluorine, like it's really small and it has a lot of electrons, so it's gonna be a little hard to steal from them. Like fluorine, the adult responsible police person it is like watching over those 7 valence electrons like a hawk. It's like, hey, I got you, and you're not leaving my sight. Lithium, it's like, oh, that one kid, it's like too far to be like bothered with. Oh, it disappeared. Oh well. Yeah. I mean, like, oh, we still have 2 more kids. It's fine. Well, I hope nobody thinks like that, but like, like for this specifically, that works really well. So with all this in mind, what do you think would have the highest ionization energy based off of what you just said?
Fluorine.
Fluorine, right? And on that same row, lithium to fluorine, which do you think would have the lowest ionization energy? Lowest first ionization energy. No. I know that, but like on that row, on that same row,
lithium,
which one would have the lowest? Lithium, right? So going from did a thing. Wait, give me a sec. Forgot to annotate. Okay, so from lithium to fluorine, the ionization energy is going up or increasing. So from lithium to francium, which one would it be easier to or kidnap kids from, francium or lithium?
Lithium.
Lithium, it'd be
Easiest.
Hey, Jeremiah, sorry,
Easy.
like
Okay,
I don't mean to rush you, but we're like kind of like a bit behind schedule, so it's like I don't know, just like let you know because like we've been on this for like quite a bit of time. Because I don't know if we'll have time for the other modules later on, but just to let you know.
Rush it.
Okay. Okay, fine. I mean, okay, quickly. So with that in mind, since there's more shells, that means that it's easier to kidnap. So that means that going from bottom to top, the ionization energy will also increase. Does that make sense?
Yeah.
All right. And then electron affinity, it's strongly correlated with electronegativity. It's basically the amount of energy that is released when it accepts an electron, right? Or the amount of energy needed for that electron. So with that in mind, which one would need the most? Or which one would release the most energy when it gets an electron? Which one can get an electron the easiest?
Fluorine.
Fluorine, right? So with that in mind, since fluorine is the easiest to get electrons with fluorine, that means that it should also be able to release the most amount of energy. Electron affinity. Okay, so with that in mind, that electronegativity, ionization energy, and electron affinity, those three are all correlated with each other. The higher the electronegativity, the higher the ionization energy, and the higher the electron affinity. Likewise, the more electronegative it is, the smaller it is. Does anybody have any questions on Module 12?
Well, we're in the chat. Someone's talking about to talk about PTSD. I don't know what that is. I'm confused.
Oh, don't worry. That has nothing to do with chemistry. It's post-traumatic stress disorder. It's just a joke. Don't worry about it.
I was confused. I don't remember anything about the Module 12.
Nah, it has nothing
Threw me
to do
off.
with it. You're good.
I'm like, oh, I just missed something.
Well,
No, it's just a joke. Who's recording?
I think it's Karina.
Oh, I thought it was Alan.
No, I just got here. I think it's Alan. Or Diego.
Oh,
I'm
sorry,
not sure.
it's Alan.
Are you recording,
Alright.
Alan?
Yes. Okay, here, let me just stop the